atoms to study and understand vehicle dynamics. So what will I be talking about? Basics of atoms, and what we focus on is the crawl, walk, run approach. How you can use atoms to start simple and then slowly build up depending on the need of the simulation you're running. So we start off with a simple spring damper model example, and then slowly move on, building up complex models, looking at complex phenomena and interaction relating to vehicle dynamics. So you start off with a simple spring damper model, look at quarter car suspensions, move to bicycle models, look at full vehicle but a four-wheel model, and then look at some advanced simulation and modeling capabilities available through atoms, specifically for vehicle dynamics analysis. We can take questions after we are done, and feel free to get back to me later on as needed. So, most of you, I hope, are familiar with atoms, but many times what I've noticed is people say, oh, I want to start building a model, and go about replicating what they physically see in the physical prototype. Building a model first, you got to understand the basics of atoms or any multi-body dynamics system. The main things that are needed to build a multi-body dynamics analysis model are parts. So these are rigid or flexible, and their main criteria is that they have mass and inertia and have initial location and orientation. Now these parts are then constrained together through joints, and then different motions or forces applied to them. Now, in addition to parts, you have geometry, and that's something that is a little different than most simple analysis tools. Parts and geometry do not go hand in hand. Geometry in atoms is used to add graphics to parts. It is an optional entity that is available for simulation. So more important for a multi-body dynamics perspective is you have the mass and inertia right, you have the constraints, that means different parts connected together right, motions, how are these two parts moving relative to each other, and then if there are any forces acting, what is the magnitude, what is the direction, so on and so forth. So the first four things are mainly used to build up a model, and then once you run a simulation, then you're requesting output from the solver, things like quantities of interest, forces, magnitudes, etc. So we start off with one of the most basic vehicle dynamics model, which is a simple spring damper system. If you look at a vehicle, look at a suspension, look at the front half or the front quarter, you have the wheel, and then you have a spring on top of it, and then masses above it, and the spring is supporting the masses. So you can, this is just a simple example where I have a rigid part and two masses associated with, and you can now carry out frequency response analysis. You can do simple things like what is the natural frequency of the system. If I excite this with a certain amplitude and frequency, what is the acceleration, velocity, displacement, etc. for the mass on top of the second spring, so on and so forth. Next, so that gives you something. It's good when you're looking at classical analysis of isolation, what is the natural frequency of system and so on. Moving on, you need to come in and look at detail. What is the geometry? What is the forces in the spring? How when I move the steering, or when the wheel moves through its jounce and rebound, how does the animation look? What are the forces? What are the magnitudes? What are the standard metrics being associated? What I'll be doing today is going back and forth between my presentation and Adam's view, so that it is not just a PowerPoint presentation, but more of a hands-on approach. And in addition, what I have done is already ran some of these analysis to save time. In this case, what I'm doing is just applying a sinusoidal input at the wheel and then looking at the toe angle. Right? Now, in this model, I have some parts. If I turn the icons on, you'll see that this is right now a kinematic model where I have a revolute joint. Because this is a rigid part, one revolute joint is sufficient to give you the the kinematics of this motion of the lower control arm. You have a spring here, and then you have a motion applied at the wheel center to mimic it going up and down. You can come in and create measures, and you can plot these measures over time. So in this example, my toe angle calculation is based on what is the change in the z direction with respect to the x direction, and a tan of that to get my toe angle for this suspension. Now, when you're building a model, you can come in and use the toolbar here to create geometry and parts, etc. That's how these cylinders are created. In addition, what you can actually do is also import CAD geometry and use that to define your parts, or if you have already created parts, enhance the graphics, or also use it to add mass and inertia computation to be more accurate. So for example, I want to now add a geometry for this upper control arm. So I can go to File, Import, and I associate this geometry with this part, upper arm. So in this case, now the geometry was created in a CAD package, and its location was nearly spot on with the hard points provided in this model. I can come in and I can either delete them or hide the So again, a geometry is a child of the part, so the part is still valid, and I can come in, and rather than having at user input, I can actually choose material so that it calculates the volume and applies inertia properties. So you can use the geometry from CAD packages to come in and get better mass and inertia from initial estimate that you had put in. Okay, so you can start, run a simulation, go into the post processor and look at different quantities of interest, toe angle, wheel. You can come in and say, now I want to plot the toe angle with respect to wheel travel. So I choose my x-axis to be wheel height. So now I get the toe change with respect to wheel travel. Okay. Again, this is a quarter car model, but you can come in, apply a motion here, and look at what is the effect of steering on this. If I have more geometry, I can look at wheel clearance, wheel envelope calculations, and so on. You can do clearance studies, etc., using the geometry. That is one example where geometry comes into play. So you can get some good results on such a simple model. I'm not really looking at a full vehicle dynamics analysis, but still these are also quantities of interest for a suspension designer. Now the next stage is a bicycle model. So you started off with a simple spring damper. You moved to a quarter car, which was more representative of the physical prototype that you have, and then now you move on to the classical vehicle dynamics models. One of the most fundamental and widely used model is the bicycle model. So it is a good model to evaluate effects, the main effects on vehicle dynamics. Things like what is the effect of the CG location, where you can calculate oversteer, understeer. How does slip at the tires affect, so on and so forth. So again, going back into view, so I'm just shutting down the graphics and then we can review the animation. So in this case, I have the front wheel, a mass, a rear wheel, and then three forces. One is driving the vehicle forward. So if I do an info on this one, there's a front just pushing the vehicle along the x-axis, and then I have a steering motion to steer the front of the front wheel, and a force to model the tire, right? So in this case, the front corner force is basically the alpha, slip, and the front slip stiffness, right? So this is just a standard value, and then the front alpha is basically the ratio of the front lateral velocity with respect to front longitudinal velocity. So again, we're using the simple building blocks of parts connected by joints and having forces and motions. This motion is the steering motion, which applies the steering. So if I animate this model, okay. Now if I go into the post processor, I can look at the steering motion applied to the front wheel and how the front and rear corner forces. You're not limited by so what you have in Adams are objects. So every part has certain characteristics that are automatically calculated by Adams view. things like position, velocity, acceleration, etc., etc. Depending on the joint, the force, torque required, so on. In addition, you can compute requests, things like what is the corner force. So you can have your own force calculations, etc., and you can plot them and place it side by side with your animation. So again, you can look, from such a simple model, you can now, what happens if I modify the stiffness. If you go to Tools, Table Editor, what happens if I change the wheelbase of the vehicle? So the front stiffness ratio, wheelbase, rear slip, hitch distance, etc. So you can create a parametric model and now understand how, the basic things like the wheelbase, mass, etc. can affect different quantities. If you change the mass, what happens? If you change the stiffness, what happens, etc. So again, you can get a lot of basic vehicle dynamics understanding out of such a simple model. So we have a two-wheeled model which kind of replicates, what happens when you steer the vehicle, what is the lateral force, what's the longitudinal force generated, etc. The next step would be when you model all your four vehicles in Adams, the four wheels in Adams, and replicate closer to a physical prototype. So in this example, we have a rover. Think of it like the Mars rover. So if you look at this model, I have the mass, a payload, I have the wheels here, and then in this thing I'm actually also modeling the suspension and the steering. By the way, this model was not built by me, I'm just using a colleague's model. But in this example, if you look closely, you have the top mount and the strut using springs to model the suspension stiffness, and a kinematic joint, a cylindrical, with motion for steering. Okay, so again, you are steering the vehicle at the front wheels, and now you can look at things like what is the spring load as it bounces over an obstacle and so on. Now this example was created for a situation where the vehicle has rigid wheels, there are no pneumatic tires. But the same approach of modeling a four-wheeled vehicle or even more wheels can be used with pneumatic tires. What Adams has, so in this example actually we are using solid-to-solid contacts, and that's one thing that may sound very easy, but getting the right contact parameters can be challenging. So you can give it a shot to get some back of the envelope numbers in, but many times it may be just easier to now, rather than using a wheel or a complicated tire force formulation, writing out the equations of motion, force equations for a tire, you instead use the tire object. So this is the same tire which is object which is also used in Adams' car and our vehicle applications. So this is available in Adams View. So this is kind of what we call a special object, wherein it not only creates the tire forces, but also creates the wheel part and accounts for all the tire characteristics. So you can say tire 1, left side, so I can say LF, mass of 25 kg, so the tire and wheel mass, inertia say 1e7, and then the Z inertia is 1e8. Now comes the interesting part, tire property file. What is that? So, in the previous example, we had a tire force which was basically slip stiffness times the slip to calculate lateral tire force, which is a simple formula, alpha times C alpha, so to say. But tires are one of the most complicated force objects in a multi-body dynamics model. So you can have a variety of different formulations that give you good enough numbers. So the choice of tire depends on the simulation, so the kind of event that you are simulating, but in addition also is used for is dependent on the data that you have. There are different tire models, and I'll now go to help. So as you can see, there are different tire models that are available. And then depending on the type of simulation, different models can be used effectively. What does this mean? Many times what we have seen is that getting tire data is difficult. So there are different tire models that are available. So you can start off with a simple formulation called a PLR tire. Again, it has vertical stiffness, vertical damping, and then slip values and so on. The next complicated one is what we call as a UA tire model. So depending on the fidelity of the tire model, the effectiveness of the tire model, the amount of data required is different. So you have a complicated one like a Pacheco tire model. So this is based on the magic tire formula written by Professor Hans Pacheco. Well, this code is not written by Hans Pacheco, but the formulation is implemented. As you can see, it has the vertical stiffness, vertical damping, but now you have things like longitudinal coefficients for the longitudinal forces. So the number of coefficients that are needed to get a good representation of a physical tire model increase. Many a times what happens is, people start off with something simple. So you have, vertical stiffness, some percentage of damping. This is pretty obvious. And then you have some, slip ratios and side slip. You can get good enough values, and then slowly move on to complicated ones depending on data availability. You can have, to generate these kind of tire property files, you have to actually go and physically test a tire, and then you fit the test data and compute these coefficients. So this is more like an empirical approach, where this is more like a physical, math expression, stiffness, damping, slip. So each tire would have a different coefficient depending on the test format and the situation it is tested on. So you can come in and pick a tire property file. Similarly, you can come in and create what we call as a road. So tire always needs a road. And now again, you can have different methods of representing a road. A road can be just a flat expanse, so 2D, and this is just for graphics, which is just a flat ground, and the force, depending on the penetration of the tire, the force is calculated. You can come in and start creating complicated tire models, road models, where you represent the road as a series of triangles. So it's more like a shell or a triangular grid. So more like elements representing the road, and the number of elements, can be increased and used. So again, so road, where does the road, my road, attached to ground, and 2D flat. Now it's create this road on the ground. In this case, my units are orientation is different. That's why the graphics created or like that. I can modify this road to have the right orientation. And similarly, now if I create a tire road wheel, now it will create a wheel part for me. So now, rather than having the connections here, I can move this object here, modify the joint, modify the motion to attach to this. And again, these are just graphics. The tire property file being used here, which is this one, is the one that gives these graphics here. So again, these are just graphics, not really needed, but do look good. So you can create a model wherein you started off with rigid contacts and replaced by pneumatic tires, based on whatever tire test data you have. Is that clear so far? So if I go back to my presentation, and apologies, I have too many windows open, but I wanted this to be more hands-on. So if I go back to my first slide, we start talking about a simple spring damper, move to a quarter car suspension, talk about a bicycle model, how a simple force is defined, talk about four-wheeled. The things in this is that you have to come in and model everything by hand. That means you got to make the left side, replicate that on the right side. You have to create your own motions to actuate the model. You have to create your own forces. You have to create your own requests, things like the toe angle request, etc. So that brings us to a specific application of Adams View for vehicle dynamics, which is the Adams Car product. So whatever you could do in Adams View, you can do most of the things in Adams Car many times more efficiently when they are specifically pertaining to vehicle dynamics. When you're talking about full vehicle models, it may be efficient to start modeling in Adams Car. Why? Mainly because it provides a specific modeling environment. It has automatic parameterization, so you can have a hard point, say for the front lower control arm, and that not only moves the arm but also moves the bushing associated at that location. It has the left-right symmetry approach, where things are symmetric between the left and right side. So if something is same, you don't have to redo the process again. Its main logic is that it's a template-based approach. That means things are broken down into subsystems. and then, like building blocks, you assemble the model together. It also has things like a driver controller to drive the vehicle around. In the previous examples, we were creating motion statements or force statements to actuate the model, get it over the bump, have it turn, etc. It also has standard metrics, things like the toe angle calculation, camber angles for suspension analysis. For full vehicle, things like the chassis yaw rate, chassis accelerations, when you're using tires, what is the normal force, what is the longitudinal force, what's the aligning moment, etc. So those are standard quantities that are calculated for every simulation. So it just makes analysis easier. So as I was saying, you have different components, and think of each of this component as an individual Adams view model. Not built in Adams view, but built in the Adams car environment, but having the same concepts. Parts connected through forces, in this case a spring, using joints, and then you have things like steering wheel motion using a driver to apply steering motion, etc. So how is Adams car different from Adams view? The structure of Adams car, as I said, has a template-based approach in which the template is not a process template per se, is more of a topology template. That means the template defines how different parts and joints fit together. It's not data. It's more of how one part is connected to other at what location, so on and so forth. Once you have a template, say for example a double wishbone, you have a lower control arm, you have an upper control arm, you have a spring in between them. Then you can take that template and add data for that specific vehicle you are working on. Say for example, masses of the lower control arm, upper control arm. Say for example, hardpoint locations, spring property files, etc. So the same vehicle, say you have a sedan and a not a station wagon, but similar kind, right? The same suspension can be now used by just changing the data associated with it. The wheelbase has increased a little bit, maybe the lower control arms have been beefed up, etc. So that's a subsystem, data associated with a particular template. And finally you have the assembly, which is combination of bunch of subsystems coming together. So steering is a template which gets specific data, gear ratio, bushings, etc. Same way for a front suspension. And now all these come together to create what we call as a final assembly. So the assembly also includes a test rig, which is the actuator to actuate the vehicle. In Adams view, you create the actuators inside your model. In here, the actuator is generally outside as a test rig. Okay? So I'll get out of view now. So when I start Adams car, typically there are two modes associated with it, standard interface and a template builder mode. A standard interface is one where you are mostly interested in changing vehicle data and running analysis, while template builder mode, or more commonly as the expert mode, is where you actually build the model. So that's more like using view or view commands to create the topology that you need. So now you have open assembly or subsystems. If I open up an assembly, it says opening assembly MDI underscore front vehicle, and then it has, you know, opening the subsystems. So front vehicle assembly is just a big listing of files that are subsystems that make up that assembly. You can have anti-roll bars. When you have a full vehicle, you'll have front suspension, rear suspension, and powertrain, brakes, chassis, etc. So it opens up. So this is the assembly. It calls front suspension subsystem, front steering subsystem, and then what it does is assembles this model together. This is a concept called communicators, which is used to assemble the whole model together, and this just warns you what communicators are not attached. So for example, since this is a half vehicle model, we don't have a body. So you can see that the subframe to body is not there. There's no body, so there's no attachment to the body, and that's why it's attached to ground, which is fine. Similarly, strut to body, anti-roll bars, we don't have an anti-roll bar, steering column to body, etc. So again, this is just a typical Adams model. Parts connected by springs, dampers, joints. Now if you look at subsystems, you see that this is just the front suspension subsystem. Look at steering, this is just the steering. And finally the assembly is the rigid wheels and the jack to move the half vehicle assembly through its motions. So that's the test rig is the one that provides the actuation. So you can come in, so in this case, I went excited my suspension through a bump and rebound travel of plus and 50 millimeters in bump and 50 millimeters in rebound. Can come in and animate this. And now if I go into the post processor, you'll see it automatically calculates a bunch of outputs, all the bushings. Now, because we are doing suspension analysis, we are more interested in the suspension kinematic and compliant quantities, right? So things like camber angle. In this case, right now, it's still, because we are doing a multi-body dynamic simulation, generally it assumes that you are simulating something in time. So the x-axis is generally time, but you can change that. And I can just surf through the different quantities. What is the caster angle change, what is the scrub radius, toe angle, etc. So you have different kinds of analysis. Parallel wheel, where both wheels move simultaneously. Opposite, where each one is in and out of phase. Roll and vertical, sweeps roll angles while allowing the wheels to find their own vertical position, keeping the total force constant. So this is most commonly used to look at roll centers, etc. Single wheel travel, steering motion, and finally you have things like static load cases. So to simulate, for example, a brake pull simulation, can come in static load. So in this example, the wheel center is held constant, and I'm applying a braking force which is at the contact patch, and looking at how, what are the suspension compliance when the steering is moved from negative 180 to positive 180. So again, you can carry out multiple analysis in one session. Because this was more with respect to time rather than wheel travel, I changed the axis back to time. What is the lateral camber compliance, etc. So these are all the suspension analysis that can be carried out. You also have an option to do a dynamic analysis to look at effect of dampers. So, apply dynamic forces and now look at the damping in the system. You can also apply not only functions, but you can have input. If you have test data in RPC format, you can input that directly at the wheel centers. One thing I didn't talk about in the standard mode yet is the adjust menu. So this is where you can come in and look at effect of hardpoint change, etc. So I can come in, move the LCA front out, and you see it automatically not only moves this geometry but also moves the bushing around with it. Similarly, I can say single, left and right, or both, and move individually. I can come in, change mass of the lower control arm, look at, I'm using one spring property file. I can come in and look at, different spring property files based on different force deflection characteristics that are available. So you can carry out all these different modifications, but you're not changing the topology much. You similarly have parameter variables. So for example, in this, now if I change the camber angle to be say 5 degrees, just to exaggerate, you can see that the vehicle moves, the wheel is inclined more, toe angle, etc. Right? So these are some of the half vehicle analysis that are possible. So generally the process we follow is you start off with some suspension, you modify it, and get the right suspension kinematic and compliance characteristics. Once you have that, you then move on to full vehicle analysis. I don't want to stretch this too long, so what I'm going to do now is actually jump a little ahead. And before talking about full vehicle analysis, I'll use the Mini Baja and Formula SAE example to showcase the full vehicle analysis. So what MSC also provides are, if you go to the MSC software webpage, Academia, Learn, Motion Learning, you will see there are example files associated. There are some pre-built examples. In addition, we provide example Formula SAE and Mini Baja databases. A question that I commonly come across is, how do you start using these? So I'll try to kill two birds with one stone by incorporating the database into my session running an analysis, and then talk about the template builder, a very, very quick intro to template builder. Okay? Let me close this session. Oh, one more thing, sorry, I forgot to add was, you have all these quantities that are available. What you also get from AdamsCar are an option to create plot config files, which are basically standard plots of important characteristics. So you can create your own plot config files once for all by setting, line width, what color, so on, all the fancy naming that you want to do, and save that as a plot config file so that you don't have to go on clicking over and over again multiple times to look at the same quantities of interest. Okay, so that's one thing. Okay, so I went to the website, clicked on this link, and then downloaded the zip file. Next I do is unzip it, and this is right here. So now I want to add this in the section and open up a Formula SAE full vehicle model. So tools, database management, add to session, come in here, pick this up. Okay. Now this is important. The alias is extremely important because that is how files are referenced. We talked about the template subsystem assembly. The way these are linked together is using the alias approach. Which database to pick which file from. In this case, the database alias is the same. And generally, this is a good idea to keep your database alias the same as a CDB. Okay. Now if I open up an assembly, earlier I just had a ACAR shared and a private, but now I have another database. And you can have multiple databases available to you in this session. Now if you see, the assembly now consists of multiple suspension subsystems, front and the rear, steering, front wheels, body, anti-roll bar, brake system, powertrain, etc. Again, the same concepts, you can modify things right here. I can come in, modify a hard point, look at the spring, etc. So now I'll just carry out a quick ISO lane change event. While it's running, so I won't be going through all these events, but there are generally 4 different classifications of these full vehicle analysis. Open loop steering, so in which the driver controller is not taking feedback of the vehicle states and applying corrective steering motion. So things like a step steer, a ramp, impulse, fish hook, single lane change, swept steer. And you can look at different vehicle characteristics, like When you do a swept steer, what is the transitional response of the vehicle? When you do ramp steer, how does the vehicle react? What is the yaw rate? What are the tire forces, etc. As you keep on increasing the steering ratio. You then have straight line events in which the vehicle is basically driven in a straight line. Things like acceleration to look at anti-lift, anti-squat properties, braking, power off straight line. You have course events like this ISO lane change where the vehicle travels a 250-meter distance. You look at yaw rate, steer responses. You can create what we call as 3D roads, which have basically an X, Y, and Z spline, and you can use that to drive the vehicle as well as steer the vehicle over. So this can be used, say a 3D road example can be used to model a parking lot, ramp. Then you have cornering events, constant radius cornering, understeer characteristics of the vehicle, etc. Finally, you also have event builder to create your own events. So you can have things like braking in a turn, but with specific characteristics like start turning at such a point when the yaw rate reaches so much, or the tire force reaches this much, etc. Right? Hopefully this simulation is done. Now if I look at, let me just clear all my pages. I accidentally deleted the whole assembly. But I don't need to rerun the simulation. I can just import the previous runs. Associate with this model. And now I can plot things like what is the yaw of the vehicle, things like the yaw rate, what is the steering wheel angle being applied to go through that path, what is the force on the rear springs, tire, normal front, normal rear, and you can see that. So you can get all these standard outputs. What was the throttle required to maintain that 120 kilometers per hour speed, etc. Right? In addition, many times you may want to set up the vehicle right. So say you just want to have the vehicle settled on the ground and look at spring preloads and ride heights, etc. So you also have an example here of, say, a static equilibrium where you just settle the vehicle. Now I come in, maybe change the spring preload. So now I ran two simulations, settle 1 and settle 2 statics, and I'm just looking at what is the chassis vertical displacement. I don't see anything because we just did a static and there's just one data point. So I can actually also plot my quantities of interest and now see that there is some effect on changing the spring preloads on the chassis displacements. So this is a very, very quick intro to different analyses. You have all these maneuvers, you have event builders, you have road builders. If you're doing smart driver events, you also have what we call as a path optimization to find the shortest distance to make the vehicle go faster. Now, to wrap up, and sorry I've gone 10 minutes over schedule, is talk about, you've seen the cake on how you can analyze things. But how do you actually build a model? The thing to remember is that templates are the ones that actually have the topology. So they provide the actuator, not the data. So start with example existing templates, which is good because you get a working baseline. You know that this thing worked, and then you start modifying it. And then standard multi-body dynamics modeling. Don't over-constrain the model. And then use hard points in construction frames, etc. to modify. So I'll just go into the template builder quickly and just show you what it is. So if you note, you have the adjust and the simulate menu. If you go to the template builder, that menu is turned off, and now you have the build menu. So Adams car comes with a bunch of example templates, and then like this Formula SAE, this also has some templates. So generally a good idea is to start with something that is already there. Say for example I start with a double wishbone, and now you basically can come in, build hard points, LCA 11. So now I just created this hard point. Similarly, I can come in, create parts, and in this case I provide the part location to be this hard point. And again, this number is just temporary number. So now I created a part. If I want to add geometry, I can come in and create a cylinder. Belonging to this part, and etc. So in here, if I modify a spring, I can now define which parts does the spring attach to. So in this example, I have a strut to body and a lower strut. So this is my lower strut part right here, and then it would attach to the body. But right now I don't have a body, so we have this concept called a mount part. So the mount part is a temporary placeholder which will be replaced by the body once the assembly is complete. You also have things like communicators. So communicators help exchange data between subsystems, right? So in this case, this is my suspension, and this needs to attach to the wheel at the wheel center. So now I have an output communicator which gives out the wheel center location so that the wheel part can come in and attach. Similarly, excuse me, you have things like ARB bushing mount. Where does the anti-roll bar bushing come in and attach to which part in the model, so on. So these communicators are used to exchange information. That kind of becomes a little advanced, and that should be a next topic on how to go about building Adams car models. but hope this gives you an idea about the modeling approach. A template builder, if I am here, I can now look at the I part, J part, and the location where the spring force is acting. If I'm in the standard interface, and if I modify the spring, I can't change between which parts the spring is acting, but what I can change is the characteristic of the spring by changing the preloads, the property file, etc. So I think that brings us to the end of the. We have additional resources available on the academic website and the knowledge base site. And now I think we can open up to questions. Sorry, I went 15 minutes overboard.
That's no problem. Before we take questions, we got a few that came in through our Q&A window, and we're grateful for those. This is Jim Ryan. I am the Academic Program Manager at MSC, and I wanted to thank Akshay for sharing his expertise with us today. We did this webinar in response to customer feedback. Many schools, professors, students who are involved with vehicle engineering have learned or heard that Adams and Adams Car are very powerful tools for these kinds of simulations, but have often asked us how do they get started, which products should they use for which types of simulations. So it was our intention today to take you from A to Z at a bird's eye view. As Akshay kind of alluded to, we couldn't get down into the details of too many of these different areas, but hopefully you've been given a big picture, if you will, of the art of the possible, as I like to call it. What can be done with Adams View, Adams Solver, Adams Car, and also hopefully have a better appreciation for how powerful but yet how complex Adams Car is. I think many of the Formula SAE teams and Baja teams and Solar Car teams, etc., salivate when they see what they can do with Adams Car. Maybe other teams are doing it, or they've seen some of our videos on our website, and they want to jump in with both feet immediately, and we're glad to try to help. But if people jump into using Adams Car without really understanding the nature of that gray box, if you will, gray meaning not completely transparent as to what all is going on behind the scenes, it can cause some frustration and problems if things don't go right and people don't know where to look, or the fact that there are parts and joints and bushings and forces and markers and things like that behind the scenes. So we recommend a crawl, walk, run approach, as always, whereby new vehicle engineers start with Adams View and Adams Solver, start with very simple, perhaps subsystems like quarter suspensions, or simple full systems like the bicycle model and the rover model that Akshay showed today. And then, and only then, after getting very comfortable with those rudimentary systems, then we can progress to using Adams Car, being much more confident that we know what's going on, and if we run into problems, how to remedy those problems and debug them. So with that, again, thank you, Akshay, for your time today. Thanks to Kent West, who's on the technical support side of things here on this webinar. And Kent, I'll turn it back over to you as kind of the host of this Q&A session, please.
Thanks, guys. Once again, I wanted to apologize to everyone for the delay in getting started. We had some confusion at the start, and I apologize for that. So, Akshay, do you want to run through the Q&A session? There were some unanswered questions. Just tell me if you want any feedback from me as to where to start. But I think you can probably see what was discussed.
Kent, if you would ask the question again, for the sake of anyone who may be not reading those questions, or just to let Akshay quickly drill down. I know there was one on what kinds of tire models to use, for instance, if you're doing like different kinds of simulations, or just four-post test rig type simulation. So if you could start there, Akshay, that'd be great.
Generally, for four-post test rig, it is recommended to use the Pacheco tire models. So if you again go to the Adams Help documentation, you will see that for four-post, they are all acceptable. Most tire models now are acceptable. Pacheco 2002 is pretty good, and so most should be okay. Now that there used to be a limit where you could not do zero forward velocity, but now that is handled by the solver. So all models are good. I would recommend Pacheco 2002 as a start. That would be the best one to start off to give you numerical stability. So that is my recommendation. Pacheco 2002.
Are tire models even required for some of the suspension simulations, wheel travel, things like that?
No, not the suspension ones. In fact, if you open up a 4-post model, you also have the option of applying directly at the wheel centers. So that in that case, you just totally do not need a tire. Any tire model is fine. Adams is actually not using that tire model in its equations of motion. It's using standard input at the wheel center and just actuating the wheel. Even in the suspension analysis, the test rig is basically just a rigid wheel. And you have, I didn't go into there, but if you open up the suspension assembly, to mimic compliance of the tire, you have tire unloaded radius and the tire stiffness. If you use a tire property file, it still picks up these two things as the quantities to apply the tire force when the contact patch is excited.
Very good. We also had another set of questions actually that came in during your session, Akshay, about can people download these files? I think you did a nice job kind of after those questions came in of taking folks to our academic website. In the Motion and Systems Learning Center, there are pre-built models such as the bicycle model and rover model for free download in the form of Adams View command files that will automatically build those models, run the simulations and post-process results, and then leave you with the models that you can analyze yourself, deconstruct, understand how they work better. And then, as he also showed, there are things like Adams car databases tailored to Formula SAE and Mini Baja vehicles there. So I highly encourage folks at their leisure after this session to go to MSC's academic website, poke around, and see what sorts of resources are available there.
In addition there, if you go to our technical support page and go to Sim Companion, you can look at, search for things like geometry, import, and car, and you'll find a KB article that walks you through how to import geometry into Adams car. I demonstrated how we did that in Adams View. Similar logic is in Adams car, and there's a KB article out there for those things.
And then last but not least, we have an online discussion forum many of you may know about already called the Adams University Forum. Great place to go ask questions or to actually search previous posts, because oftentimes many of the most common questions for new people have already been asked and answered by experts in the forum. So search first. If you don't find anything, then go ahead and ask a question of your own.
Any more? Yeah, I'm try to be as active as I can be on the forum. So if you have any questions, feel free to post them on the university page or the full simulation page, or if Adams car related, the Adams car section, and I'll do my best to answer those as best as I can.
And it's nice to know that there are engineers in industry, vehicle dynamics experts who have been using Adams for decades actually, who are courteous and kind enough to lend their expertise there, and actually are on the lookout for young dynamicists, young vehicle engineers who are using Adams and Adams car. They might want to hire you. So it's a good opportunity for you to build up your resume if you're a student and want to do this sort of work after graduation. Certainly, Adams car is used by most of the world's premier automotive manufacturers in every part of the world.
Actually, I was wondering if you might want to speak briefly about the tire models again. I posted a comment into the Q&A session or the chat window. I posted a comment into the chat window that in general it seems as though there are some tire models where you've got the simpler tire models, quote, simpler tire models have more inputs that are more intuitive, whereas the more complex models have a lot more inputs. I was wondering if you might want to briefly say something about the new tire test rig functionality that will allow you to generate tire coefficient data, perhaps?
Yep. In the last MD Adams R3 release, we have the tire test rig, which is basically a standalone model where you select a tire property file, apply the mass and inertia of the wheel tire, and then look at various inputs, things like, what's the longitudinal velocity. So basically mimic a tire test rig on the physical. Once you run that, you can get the tire property curves for different load cases, etc. And in the next release of Adams, or the latest MD 2010, we also have a tire fitting tool. So if you have test data or if you have existing tire models, you start off with something extremely simple like this. You know the vertical stiffness, you know the damping. You can create a virtual test rig, create your force plots, and then use these curves to fit a Pacheco coefficient. Once you have this is a much this is a high fidelity model and has a lot more versatility in its use. It's used for combined force moment calculations, combined slip calculations, etc. It has things like relaxation effects, pneumatic trail, etc. So all these fancy computations are available in this Pacheco model, but you need not have all the data to start off. So you may estimate these numbers or get some simple test data, do a virtual test, take these curves, and then fit these curves to get this final fancy Pacheco 2002. Or the option is take your tire, go to a tire testing facility, and they will give you these coefficients. Ken, does that answer?
Yeah, thank you. Because I think there's a common question from academic people that are saying, how do I get tire coefficients that make sense? My manufacturer's given me some stuff. How do I get coefficients that make sense? So I think that new fitting tool that's in the next release of Adams, I think that will be very interesting.
Yeah, I'm just trying to open it up.
Thanks.
In the interest of time, I think we're going to make this our last question, if that's okay with you guys. While Akshay is bringing this up, I'm just going to remind people that today's session was recorded and will be available for replay if you would like to come back and view it again later, or if you'd like to refer your colleagues or teammates to come view it on their own convenient time. And I also encourage you to keep an eye out for future Sim Academy webinars. We're constantly trying to have new sessions to help our customers make the most of our software.
Yes, thank you very much for your attendance.
One last thing, Akshay, you want to close with this?
No, I won't run through this right now. It will take some time. So.
Okay.
But this is the tire fitting data tool that will generate a Pacheco coefficients. So things like, these numbers should be available to you from your, tire suppliers. And then you just, run a test rig and use the test data to fit these curves in. Actually, if you look at our knowledge base site, there would be an example that shows how to use the tire data fitting tool, and I'll maybe post that to Kent and Jim so that they can upload it to. I'll update my presentation with that link to this tire data fitting tool.
Terrific. Thanks again, fellas. Thanks to our audience members. Take care.
Okay, thanks.
I know.